Throughout the ages, humanity has peered into the darkness above, seeking answers to questions that have haunted us since we first gazed upward. Scientists have unraveled countless cosmic enigmas through meticulous observation and rigorous experimentation. Yet one of the most profound mysteries has remained tantalizingly out of reach, hiding in plain sight. We have never witnessed the birth of a solar system like our own. Our understanding of how planetary systems come into existence relies heavily on indirect evidence, extrapolations drawn from ancient meteorites that have plummeted to Earth, and observations of the planets that circle our sun today. For the most part, the scientific community believes we've constructed a reasonably accurate picture, at least in broad strokes. The models we've developed appear to hold together logically, fitting the pieces of evidence we've managed to gather. However, certain stages in this grand cosmic narrative have remained frustratingly obscure. The precise mechanisms of how, when, and where planets actually form have eluded direct observation until now. Earlier this year, the James Webb Space Telescope made a discovery that would fundamentally alter our perspective. Deep within a cocoon of gas and dust, the observatory detected a newborn star, and within that stellar nursery, something extraordinary was taking place. Among the swirling clouds of material, planets were beginning their long journey into existence. For the first time in human history, we're able to observe the very earliest phases of planetary formation as they unfold. We're not just filling in gaps in our theoretical framework, we're witnessing the actual process that gave birth to our own world billions of years ago, watching the cosmic events that ultimately led to our existence. Today, we'll explore the remarkable discovery of HOPS 315. Examine what its future planetary family might look like, and consider how this breakthrough is transforming our understanding of how worlds come to be throughout the cosmos. Given that we inhabit a planet ourselves, have sent spacecraft to explore 7 others in our solar system, and have detected more than 6,000 worlds orbiting distant stars, you might reasonably assume that we possess a comprehensive understanding of planetary formation. The reality, however, is far more complicated. The majority of our current knowledge stems from detailed analysis of meteorites that have survived their fiery descent through Earth's atmosphere and careful study of the planets in our solar system as they exist today, billions of years after their formation. Everything else, the dynamic processes, the transformative moments, the critical transitions, has been left to theoretical models and computer simulations. Why this significant gap in our understanding? The answer lies in the nature of stellar and planetary birth itself. The early stages of these processes are extraordinarily difficult to observe directly. The entire cosmic drama begins with massive molecular clouds, vast collections of dust and gas particles drifting through interstellar space. Within these clouds, particles move and collide, generating thermal pressure that pushes outward against the structure of the cloud. Simultaneously, these same particles must obey the fundamental laws of gravity that govern all matter in the universe. They pull on each other, drawing the cloud inward. This delicate interplay between outward pressure and inward gravitational attraction persists in perfect equilibrium for millions of years, maintaining the nebula in a stable state. But the universe is a dynamic place, and stability never lasts forever. A nearby cosmic catastrophe, perhaps the violent shock waves emanating from a supernova explosion, can suddenly disrupt this ancient balance. When gravity begins pulling the gas cloud inward more forcefully than the pressure from particle motion can resist, a runaway effect initiates what astronomers call gravitational collapse. Material from the outer regions of the cloud begins falling inward like rain. As everything compresses together, growing denser and hotter, the cloud begins to rotate faster and faster, accelerating in the same way a figure skater spins more rapidly when pulling their arms close to their body. A temperature gradient establishes itself within the collapsing cloud. Near the center, within a region roughly the size of Earth's orbit around the Sun, what astronomers call 1 astronomical unit temperatures soar to more than 1,000 Kelvin. Further out, at a distance of 5 astronomical units, the temperature drops to around 400 Kelvin. Over approximately 100,000 years, the majority of the cloud's mass concentrates in the middle, eventually forming what we call a protostar. The remaining material disperses outward, creating a protoplanetary disk of swirling dust and gas, a cosmic womb nurturing this stellar embryo. This abundance of gas and dust makes the stellar formation process incredibly challenging to observe. Our telescope simply cannot penetrate through the dense veil of material. However, as technology has advanced over recent decades, we've begun catching fleeting glimpses of what lies hidden within. In 2013, a research team led by Amelia Stutz directed the Herschel Space Telescope toward the Orion Molecular Cloud Complex, the largest star-forming region in the vicinity of our solar system. This observational campaign, known as the Herschel-Orion Protostar Survey, abbreviated as HOPS, focused on the Messier 78 Nebula. The survey identified 15 previously unknown protostars, each possessing between 1/5 and twice the mass of our Sunday. These stellar infants had remained invisible to earlier observations because their surrounding gas envelopes are remarkably cold, heated to merely 20 degrees above absolute zero, with the protostars themselves buried deep within. This frigid temperature indicates that the nascent star hasn't yet had sufficient time to warm its surrounding material. These are truly young objects. Stutz and her colleagues believed they had discovered some of the youngest protostars ever detected, finally providing real-world data against which theoretical models could be tested. But understanding the initial formation of stars represents only part of the puzzle. The process by which planets themselves emerge from these disks remains equally mysterious. Our computer simulations suggest that within the main body of the protoplanetary disk, dust and gas particles begin to stick together. They condense into microscopic solid particles, which gradually clump together into progressively larger grains over millions of years. Eventually, these solidifying aggregations of spinning debris evolve into planetesimals, the fundamental building blocks of primordial planets, objects spanning several kilometers across. If sufficient planetesimals come together, whether through gravitational attraction or direct collisions, they can assemble into a planet. The fundamental problem is that we've never actually witnessed most of this process occurring. We've discovered young planets. One exoplanet boasts 4 times Jupiter's mass while being less than 5 million years old, and another gas giant orbits a star that formed merely 2 million years ago. But these represent the earliest planetary systems we've found, and they're already complete, fully formed worlds. There exists a gap of hundreds of thousands, perhaps millions of years that we've never been able to observe. That vast temporal void in our understanding persisted until very recently, 1,300 light-years distant. In the Orion Nebula, a baby solar system is coming into being, and we're watching this cosmic birth unfold with our own eyes. Well, through James Webb's sophisticated instruments. This system is designated HOPS 315, a star that has existed for less than 150,000 years and contains approximately 6/10 the mass of our Sunday. It's still actively growing, feeding on an envelope of dust and gas that shrouds it in a cloudy veil. Incredibly, researchers identified a gap in the obscuring clouds and managed to capture images of what lies within. What they observed was nothing short of extraordinary. Webb's infrared spectroscopy revealed the presence of both warm silicon monoxide gas and tiny silicate crystals in the vicinity of this young star. We were witnessing the moment when gas condenses into solid material for the first time, capturing the very instant when the building blocks of planets begin to form. This discovery carries profound significance because, as a protoplanetary disk gradually cools, chemical compounds begin crystallizing in a specific, predictable order determined by their condensation temperatures. Scientists refer to this as the condensation sequence. We can infer this sequence through our understanding of chemistry and our detailed analyses of primordial asteroids, which serve as time capsules preserving conditions from our early solar system. The most ancient condensates trapped within these asteroids are calcium-aluminum inclusions, known as CAIs, along with crystalline silicate materials. The fact that we detected both silicon monoxide gas and solid crystalline silicates surrounding HOPS 315 indicates that this star and its emerging planetary system occupy the very beginning of their formation timeline. In other words, we were observing the very first stage of planet formation as it happens in real time for the first time in human history. This represented a major breakthrough in planetary science. As Melissa McClure, the lead author of the landmark research paper, eloquently stated, "For the first time, we've identified the earliest moment when planet formation is initiated around a star other than our Sunday." The research team wanted to probe deeper into this discovery, so Professors Melissa McClure and Merel Van Hoff focused another powerful instrument on this infant star, the Atacama Large Millimeter, Submillimeter Array Telescope. known as ALMA. While the James Webb Space Telescope revealed the warm inner regions of the young system through infrared light, ALMA specializes in observing much colder material, the dust and gas that emit millimeter and submillimeter wavelengths of electromagnetic radiation. This capability allows astronomers to trace the chemical composition and structural characteristics of molecular clouds with remarkable precision. By combining observations from these two observatories, McClure and Van Hoff could connect previously separated pieces of the puzzle. James Webb provided evidence of early planetary formation occurring, while ALMA pinpointed the exact location within the disk where this transformative process was taking place. What makes this particularly intriguing is that the region where planet formation is beginning around HOPS 315 corresponds roughly to the same distance from the star as the region around our Sun where asteroids of similar composition are found today. We don't yet fully understand the implications of this correlation, but it strongly suggests that the same early construction steps for planets may occur across many young stellar systems throughout the galaxy. But there's more to this story. It's worth noting that although silicates were detected, the outflow jet that researchers studied contained surprisingly little silicon, the most crucial element for creating silicates, and by extension, planets. The measurements showed only 2% of the silicon that McClure expected relative to the amount of carbon present. However, this silicon deficiency isn't necessarily problematic for planet formation. In fact, it might be quite the opposite. McClure suggests that may be a hint that planetesimals are already forming there in a similar way that they must have in our solar system. This represents an intriguing finding considering how remarkably young this system is. We are finally able to timestamp the beginnings of planetary formation to less than 150,000 years after a star begins coalescing, a discovery that's fundamentally challenging our existing models. Initially, astronomers believed that gases only began condensing after the central star evolved into what's classified as a Class II system, the stage when the stellar envelope has mostly dissipated. The star has ceased growing, and what remains is a relatively calm, well-organized debris disk. However, over the past decade, mounting evidence from several young protostars has suggested that planet formation actually initiates much earlier in the stellar development timeline. Still, these early disks were not well characterized or understood. HOPS 315 has provided definitive confirmation of this suspicion. Yet one mystery about the nebular hypothesis continues to perplex scientists. Researchers have long struggled to explain how millimeter-sized particles called chondrules grow into rocks kilometers in diameter. Small particles don't naturally adhere to each other effectively, and medium-sized objects tend to spiral into the central star within approximately 100 years due to gas drag, a phenomenon where friction with the surrounding gas causes orbital decay. One proposed solution suggests that dust collapses in pockets of gravitational instability, directly forming planetesimals, essentially a rock emerging fully formed from a cosmic sandstorm. By repeatedly observing how the ratio of gas to solid material changes in HOPS 315 over time, scientists can uncover how rapidly solids grow within the inner disk, identify factors that might limit their coalescence, and determine how these processes affect overall planetary development. But perhaps the most impactful aspect of this discovery is that the HOPS 315 system represents one of the best natural laboratories we know of to actually investigate some of the processes that occurred in our own solar system billions of years ago. By comparing the dust chemistry observed in HOPS 315 with the composition of meteorites that have fallen to Earth, scientists can determine whether the same condensation sequences and elemental distributions that shaped our planets occur in other regions of the universe. We can finally test our theoretical models against actual observations of planetary formation in progress, comparing our predictions with reality unfolding before our eyes. But as with every significant discovery in science, answering one question inevitably generates numerous others. What does the future hold for HOPS 315? How many planets will eventually orbit this young star? Will they be divided into small, rocky worlds in the inner regions and massive, icy gas giants in the outer reaches of the star's gravitational influence? Similar to the architecture of our own solar system, the condensation sequence occurring within the protoplanetary disk exerts a direct influence on what types of planets form and where they ultimately reside. This relationship allows us to make educated predictions about HOPS 315's future planetary family. Since the early disk doesn't maintain uniform temperature throughout its extent, different chemical compounds will condense first in different locations. One particularly important feature of this temperature gradient is called the snow line, the distance from the star beyond which conditions become cold enough to allow water, ice, and other volatile compounds to form solid particles. In our early solar system, this critical boundary existed at approximately 2.7 astronomical units from the Sun, well beyond the orbit of Mars but interior to Jupiter's current position. Beyond this snow line, ice and dust accumulate together, slowly snowballing into progressively larger aggregations that eventually become giant planetary cores. The colder temperatures in these outer regions also mean that gas molecules move more slowly enough to be gravitationally captured by the growing cores of these frozen worlds. Eventually, enough gas accumulates around these cores to form a complete planet, and a gas giant is born. This process occurs remarkably quickly by cosmic standards. Scientists believe this is how Jupiter and Saturn formed in as little as 10 million years, a mere blink of an eye in astronomical terms. Meanwhile, on the warmer side of the snow line, ice and volatile compounds are completely vaporized by the heat radiating from the forming star. In these inner regions, only materials with exceptionally high melting points can survive in solid-form substances like iron, nickel, aluminum, and various rocky silicates. By the time these inner worlds begin serious formation, most of the gas in the system has already been captured either by the growing central star or by the rapidly forming gas giants in the outer system. This means there's almost no gas remaining available for these slower developing inner worlds to capture. The result is smaller, rocky planets, like the ones we observe in our inner solar system: Mercury, Venus, Earth, and Mars. These terrestrial worlds lack the massive gas envelopes of their outer siblings because they formed in a region where volatile materials couldn't exist and where the available gas had already been claimed by larger, faster-forming bodies. We cannot yet determine exactly how many planets will eventually form around HOPS 315, but based on our understanding of planetary formation processes, we would expect to see a configuration similar to our own solar system, inner rocky worlds closer to the star and outer gas giants farther away. Although we still cannot entirely rule out the possibility of planetary migration and the formation of hot Jupiters gas giants that somehow end up in very close orbits around their parent stars, defying the simple temperature-based formation model. Given that the current early stages of planet formation are occurring at approximately the same location as our asteroid belt relative to our Sun, one fascinating question emerges. Will HOPS 315 eventually develop its own asteroid belt? Our asteroid belt occupies the space between 2.2 and 3.2 astronomical units from the Sun, and we've already established that asteroid belts are not unique features of our solar system. In 2001, researchers discovered the first asteroid belt outside our solar system, located 70 light-years away around a star called Zeta Leporis, a star approximately 1,000 times older than HOPS 315. But whether an asteroid belt develops around this infant star depends on several interconnected factors, particularly the formation history of planets in that region. We have our asteroid belt primarily because of Jupiter's influence and the specific timing of its formation. Initially, the region between Mars and Jupiter contained abundant dust and planetesimals, plenty of raw material to assemble another terrestrial planet. Under different circumstances, a fifth rocky world might have formed there. But once Jupiter coalesced and began growing, it became massive extraordinarily quickly. That immense gravitational influence and the orbital resonances it created disrupted the surrounding region, preventing the smaller bodies from continuing their accretion process and trapping planetesimals in stable orbits around the sunday. This gravitational interference left behind a population of primordial space debris that never coalesced into a unified planet, instead becoming the asteroid belt we observe today, a permanent reminder of a planet that never came to be. So one pathway for HOPS 315 to end up with an asteroid belt would be for it to create a planet with sufficient mass to cause a gravitational disturbance similar to Jupiter's effect on our solar system. However, if a sufficiently large planet never forms in that region, HOPS 315 could end up with an intermediate-sized world near the snowline, something our own solar system never developed, perhaps because Jupiter's rapid formation prevented it. In essence, HOPS 315 serves as a portal to our past. Studying this young system is analogous to observing our own solar system as it existed 4.6 billion years ago, when Earth was still nothing more than a dispersed cloud of gas and microscopic dust particles slowly beginning to coalesce. But this discovery also raises profound questions that extend far beyond this single system. How common are solar systems like ours throughout the galaxy and the broader universe? Does planet formation consistently begin at approximately 2.2 astronomical units from the central star, or does this distance vary significantly based on the star's mass and other factors? How rapidly does the protoplanetary disk transition from microscopic dust particles to kilometer-sized planetesimals? What determines whether a system develops multiple large planets or numerous smaller worlds? To answer these fundamental questions, researchers are eager to expand the search to encompass more very young stellar systems, hoping to identify other stars similar to HOPS 315 that can be observed during these critical early stages. If multiple systems exhibit the same characteristic signatures of nascent planet formation, we'll have discovered a protoplanetary goldmine, a wealth of observational data to analyze and compare, helping us better understand not just how planets form, but how our own world and solar system came to exist. The implications of the HOPS 315 discovery extend even further than mapping the formation timeline of planets. This observation provides crucial insights into the chemical processes that determine planetary composition, the very elements and compounds that make up the worlds themselves. When we examine meteorites that have survived from the earliest days of our solar system, we find they contain distinct chemical signatures, fingerprints of the conditions under which they formed. These ancient rocks reveal that different materials condensed at different temperatures and locations within the early solar nebula. The hottest regions, closest to the forming sun, saw the condensation of refractory material substances that require extremely high temperatures to vaporize, such as calcium, aluminum, and titanium compounds. Moving outward from the sun, progressively more volatile materials could condense as temperatures decreased. Iron and nickel condensed into metallic grains. Silicate minerals formed rocky particles. Further out still, beyond the snow line, water ice became stable, followed by even more volatile ices, methane, ammonia, and other compounds that only remain solid at very low temperatures. This chemical gradient fundamentally shaped what types of planets could form in different locations. The inner solar system, being too hot for ice to survive, could only assemble planets from refractory and rocky materials, hence our small, dense terrestrial planets. The outer solar system, with its abundance of ice in addition to rock and metal, had far more building material available, allowing the formation of massive planetary cores that could capture thick atmospheres of hydrogen and helium. The observations of HOPS 315 suggest this same chemical gradient is establishing itself in that young system right now. The silicon monoxide gas and crystalline silicates, detected by James Webb, are forming in the warm inner regions, while ALMA's observations of the colder outer disk show different chemical compositions more appropriate to those lower temperatures. This chemical stratification isn't just an interesting scientific curiosity, it's a fundamental aspect of how solar systems develop their characteristic architecture. Understanding this process helps explain not only how our solar system formed, but also the incredible diversity of exoplanetary systems discovered in recent decades. Some exoplanetary systems look nothing like ours. Hot Jupiters, gas giants, orbiting extremely close to their parent stars, seem to violate the simple temperature-based formation model. How could a massive gas planet form so close to its star, where temperatures should be far too high for ice to exist, and where there shouldn't be enough solid material to build a large planetary core? The answer likely involves planetary migration planets forming farther from their stars and then gradually spiraling inward due to gravitational interactions with the protoplanetary disk or with other planets. Observing systems like HOPS 315 during their formation might eventually help us understand under what conditions such migration occurs and how common it might be. Other exoplanetary systems contain types of planets we don't have in our solar system at all. Super-Earth's rocky planets larger than Earth but smaller than Neptune appear to be incredibly common throughout the galaxy. Yet, our solar system lacks any examples. Many Neptunes, smaller versions of the ice giants in our outer solar system, are also abundant around other stars. Why didn't our solar system produce these intermediate-sized worlds? By observing multiple young stellar systems during their planet-forming phase, astronomers hope to identify the factors that determine what types of planets a system produces. Is it the mass of the central star? the total amount of material in the protoplanetary disk, the specific chemical composition of the disk, the presence or absence of nearby stellar companions that might gravitationally perturb the forming system, or perhaps the timing of when the central star ignites nuclear fusion and begins generating strong stellar winds that blow away remaining gas. HOPS 315 represents just the beginning of what could become an extensive observational campaign to study planetary formation in real time across many different stellar environments. The James Webb Space Telescope and ALMA are both capable of observing numerous other young stellar systems with similar sensitivity, potentially building a comprehensive database of forming planetary systems at various stages of development. Imagine having observations of dozens or even hundreds of systems like HOPS 315, each caught at slightly different moments in their formation timeline. Some might show the very first condensation of gas into solid particles, as HOPS 315 does. Others might be slightly more evolved, with clear evidence of planetesimal formation. Still, others might show early planets already clearing gaps in their protoplanetary disks. By assembling this temporal sequence from multiple systems, astronomers could effectively create a time-lapse movie of planetary formation, watching the process unfold step by step, even though each individual system takes millions of years to evolve. This would be analogous to how biologists might study human development by observing many different individuals at various ages, from embryo to adult, rather than following a single individual for their entire lifetime. Such a comprehensive observational database would allow scientists to test theoretical predictions with unprecedented rigor. Current models of planet formation make specific predictions about how quickly various processes should occur, what chemical signatures should appear at different stages, and how the disk's structure should evolve over time. With enough observations of real systems, we could verify which predictions prove accurate and which require revision. The discovery also highlights the crucial importance of multi-wavelength astronomy, observing the same objects with different types of telescopes that detect different portions of the electromagnetic spectrum. James Webb, operating in the infrared, could see the warm inner regions of the HOPS 315 disk where silicon-based minerals were condensing. ALMA, detecting millimeter and submillimeter radiation, could map the colder outer regions and trace different chemical species. Neither instrument alone would have provided the complete picture. The infrared observations might have detected the silicate crystals, but couldn't have mapped their distribution throughout the disk or detected the colder outer regions. The millimeter observations could have mapped the disk structure, but might have missed the warm inner chemistry where the earliest condensation occurs. This complementary approach will become increasingly important as astronomers study more young stellar systems. Different telescopes and instruments provide different pieces of the puzzle, and only by combining observations across the electromagnetic spectrum can we develop a comprehensive understanding of the complex, multifaceted processes occurring in these systems. The ongoing evolution of HOPS 315 itself presents exciting opportunities for future observation. This system is so young that it will continue evolving significantly over the next several years and decades, timescales short enough that human astronomers can potentially observe real changes occurring. By monitoring HOPS 315 repeatedly over time, researchers can track how the chemical composition of the disk changes as more gas condenses into solids. They can measure how quickly the solid material accumulates and whether it begins clumping together into larger bodies. They can observe whether the disk develops any gaps or rings, features that might indicate forming planets are already beginning to clear out their orbital paths. This kind of temporal monitoring would provide invaluable insights into the dynamics of planet formation. How quickly do these processes occur? Do they proceed smoothly and continuously, or do they happen in sudden bursts driven by instabilities in the disk? These are questions that computer simulations can attempt to answer, but nothing beats actual observations of a real system evolving over time. The HOPS 315 discovery also underscores the value of studying our own solar system's small bodies, asteroids, comets, and meteorites as historical records of our system's formation. Every meteorite that falls to Earth carries information about the conditions under which it formed, information encoded in its chemical composition, mineral structure, and isotopic ratios. By comparing these ancient relics from our solar system's birth with observations of young systems like HOPS 315, scientists can verify whether the processes we infer from meteorites actually match what we observe happening in real time elsewhere. This cross-validation strengthens our confidence in the conclusions we draw about our own solar system's history. For instance, Certain meteorites contain tiny grains that formed before our solar system even existed, presolar grains that originated in other stellar systems and somehow survived incorporation into our solar nebula. These grains have distinctive isotopic signatures that differ dramatically from solar system materials, marking them as immigrants from elsewhere in the galaxy. Understanding how such grains could survive the violent processes of solar system formation requires detailed knowledge of those processes. Observations of systems like HOPS 315 help constrain the temperatures, pressures, and timescales involved, which in turn helps scientists determine under what conditions presolar grains could remain intact rather than being vaporized and incorporated into the general solar nebula material. The presence of these presolar grains in meteorites tells us something profound about the interconnectedness of stellar generations. The material that formed our solar system wasn't pristine, it was already enriched with elements created in previous generations of stars. When those ancient stars died, some violently as supernovae, they scattered their fusion products into space. That enriched material eventually became part of the molecular cloud that collapsed to form our sun and planets. Observing young stellar systems like HOPS 315 inches regions of active star formation like the Orion Nebula reminds us that this cycle continues. The stars forming today are incorporating material from previous stellar generations, just as our sun did. And billions of years from now, when our sun exhausts its nuclear fuel and dies, it will return much of its material to the interstellar medium, enriching future molecular clouds that will collapse to form new generations of stars and planets. This cosmic recycling of matter connects us to the broader history of the galaxy and the universe. The atoms in our bodies, the carbon in our DNA, the calcium in our bones, the iron in our blood were forged in the cores of ancient stars and scattered into space when those stars died. We are, quite literally, made of stardust, as the famous saying goes. But we're not just made of stardust, we're made of planet-forming material that followed the same physical and chemical processes we're now observing in HOPS 315. The philosophical implications of this discovery extend beyond the scientific details. For the first time, we're watching worlds being born. We're observing the initial steps of a process that will eventually, if given enough time and the right conditions, produce planets. And on at least some of those planets, conditions might prove suitable for life to emerge and evolve. When we look at HOPS 315, we might be seeing the birthplace of future living worlds. We can't know whether life will eventually emerge in that system. The probability of life arising on any given planet remains deeply uncertain, as we have only one example to study life on Earth. But the basic ingredients appear to be common throughout the universe. Water, so crucial to life as we know it, is one of the most abundant molecules in the cosmos. Organic compounds, carbon-based molecules, including some of the building blocks of life, have been detected in molecular clouds, in comets, in asteroids, and in the atmospheres of planets and moons throughout our solar system. The chemical elements necessary for life, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, are produced in stars and distributed throughout the galaxy. If planets form around HOPS 315 following similar processes to those that formed our solar system, and if some of those planets end up in the habitable zone, the region where liquid water can exist on a planet's surface, then the basic prerequisites for life as we know it would be in place. Whether life actually emerges would depend on factors we don't yet fully understand, but the potential would exist. This perspective transforms our view of planetary formation from an abstract astrophysical process into something more profound, the creation of potential homes for life, places where the universe might eventually contemplate itself through conscious beings, as it does through us here on Earth. The discovery of HOPS 315 and the ability to observe planetary formation and progress also carries implications for how we think about humanity's place in the cosmos. For thousands of years, humans believed Earth occupied a special, central position in the universe. The Copernican revolution displaced us from that central position, showing that Earth orbits the Sun rather than the reverse. Subsequent discoveries have continued this process of cosmic humbling. Our Sun is just one ordinary star among hundreds of billions in the Milky Way galaxy. Our galaxy is just one of hundreds of billions, perhaps trillions of galaxies in the observable universe. The physical laws that govern Earth apply equally everywhere else. The chemical elements that compose our world exist throughout the cosmos. And now we know that the processes that formed our solar system and our planet are not unique or special. They're occurring in countless locations throughout the galaxy and the universe. The existence of Earth and the other planets in our solar system doesn't represent a cosmic miracle or an extraordinarily rare occurrence. It's the natural outcome of physical processes that happen regularly wherever the right conditions exist. This realization simultaneously humbles us and connects us to the broader cosmos. We're not cosmically special, but we're not alone either, at least not in terms of being products of planetary formation processes. Whether we're alone in terms of being the only intelligent life in the universe remains an open question, but the ubiquity of planets and planetary systems certainly suggests that if life can emerge on planets with suitable conditions, it might have done so in many locations. The technical challenges overcome in observing HOPS 315 also deserve recognition. Penetrating the dense cocoons of gas and dust surrounding very young stellar systems requires extraordinary sensitivity and the right observational capabilities. The James Webb Space Telescope's infrared instruments are particularly well suited to this task because infrared light can penetrate dust clouds that completely block visible light. This is why Webb has proven so revolutionary for studying stellar and planetary formation. Previous telescopes, operating primarily at visible wavelengths, could only see the outer edges of these dust cocoons. Webb can peer through the dust and observe the warm inner regions where crucial processes occur. Combined with radio observations from ALMA that map the cold outer disk, we now have an unprecedented ability to study these systems comprehensively. The development of these observational capabilities required decades of technological advancement and billions of dollars of investment in space telescopes and ground-based observatory arrays. The James Webb Space Telescope, launched in late 2021, represents the culmination of more than 20 years of development and represents one of the most complex scientific instruments ever constructed. ALMA, consisting of 66 radio telescopes working together as an interferometer at an altitude of 5,000 meters in the Chilean Andes, required international collaboration and overcoming significant engineering challenges to construct and operate. These facilities represent humanity's commitment to understanding the universe, our willingness to invest enormous resources into answering fundamental questions about existence and our cosmic origins. The scientists involved in studying HOPS 315 are also part of a long tradition of astronomical investigation, stretching back centuries. From Galileo pointing his crude telescope at Jupiter and discovering its moons, to William Herschel discovering Uranus and infrared radiation, to Edwin Hubble revealing the expansion of the universe, to the modern era of space telescopes and planetary missions, each generation builds on the discoveries of previous ones, gradually assembling a more complete and accurate picture of the cosmos. The study of HOPS 315 continues this tradition, answering questions that previous generations could only speculate about. Scientists in the early 20th century developed the basic framework of the nebular hypothesis, the idea that solar systems form from collapsing clouds of gas and dust, but they had no way to directly observe the process. They could only infer it from theoretical reasoning and indirect evidence. Now, a century later, we can actually watch it happening. We can test the predictions made by those early theorists and verify which aspects they understood correctly and which require modification. This represents scientific progress in its purest form, moving from speculation to observation, from hypothesis to verified fact. As we look toward the future, the study of HOPS 315 and similar young stellar systems will likely become an increasingly important area of astronomical research. The James Webb Space Telescope and ALMA are both relatively new facilities, with long operational lifetimes ahead of them. Over the coming years and decades, these instruments will observe numerous young stellar systems, building the comprehensive database necessary to fully understand planetary formation in all its diversity. Future space telescopes currently in planning stages may provide even more powerful capabilities. Proposed missions would have larger collecting areas, higher sensitivity, and enhanced imaging capabilities compared to current instruments. Ground-based telescope technology continues advancing as well, with extremely large telescopes featuring mirrors 30 to 40 meters in diameter currently under construction in Chile and Hawaii. These future instruments will allow astronomers to study planetary formation in even greater detail and at greater distances. They might detect individual forming planets directly, rather than just inferring their presence from gaps in protoplanetary disks. They might be able to measure the chemical composition of forming planets' atmospheres, tracking how these atmospheres evolved during planetary formation and early development. They might even be able to study planetary formation around different types of stars, not just sun-like stars, but also smaller red dwarfs and larger blue giants, to determine how stellar mass influences the planetary formation process. Understanding these variations would help explain why different stellar systems end up with such diverse planetary architectures. The theoretical side of planetary formation research is also advancing rapidly. Modern computer simulations can model the complex physics involved in protoplanetary disk evolution, from the turbulent flow of gas, to the collisional dynamics of solid particles, to the gravitational interactions between forming planets. These simulations are becoming increasingly sophisticated as computational power increases and our understanding of the relevant physical processes deepens. By comparing detailed simulations with observations of real systems like HOPS 315, scientists can refine their models and improve their predictive power. When simulations successfully reproduce what we observe in real systems, we gain confidence that we understand the underlying physics. When simulations and observations disagree, it indicates gaps in our understanding that require further investigation. This iterative process of observation, simulation, comparison, and refinement represents the heart of the scientific method applied to complex systems that we cannot directly experiment on. We cannot create a solar system in a laboratory. We cannot fast-forward time to watch planet formation complete in a human lifetime. But we can observe many different systems at various stages, build computer models that capture the essential physics, and gradually converge on a complete understanding of how planets form. The story of HOPS 315 also reminds us of the importance of scientific curiosity and the human drive to understand our origins. These observations serve no immediate practical purpose in the sense of solving urgent problems facing humanity. They won't cure diseases, end poverty, or prevent conflicts. Yet they fulfill a fundamental human need, the need to understand where we came from and how we fit into the larger cosmos. This drive to understand has characterized humanity throughout our history. Ancient peoples created creation myths to explain the origin of the world. Philosophers pondered the nature of the cosmos and our place within it. Scientists developed increasingly sophisticated methods to probe reality and test their ideas against evidence. Each generation inherited the knowledge of previous generations and added to it, gradually building the remarkable edifice of modern scientific understanding. The discovery that we can now observe planetary formation in progress represents the latest chapter in this ongoing story. Future generations will build on this foundation, making discoveries we cannot yet imagine with technologies not yet invented. They will answer questions we haven't yet thought to ask, but they will do so standing on the shoulders of today's astronomers who pointed their telescopes at HOPS 315 and revealed its secrets. As we contemplate the young star HOPS 315 and the planets gradually coalescing from the dust surrounding it, we're confronted with a profound temporal perspective. The light we're observing from that system left the star 1,300 years ago, during Earth's medieval period. The system we're seeing is not as it exists today, but as it existed in what we might call the system's ancient history, though for such a young system, even 1,300 years represents a significant fraction of its total age. By now, in the system's present moment, which we won't observe for another 1,300 years, planetary formation has progressed significantly. Planetesimals may have already formed. Perhaps small protoplanets are beginning to coalesce. The system is evolving and developing, but we remain frozen in time, watching events that are already ancient history by the time the light reaches us. This light-speed delay reminds us of the vastness of space and the limitations inherent in astronomical observation. We can never see cosmic objects as they exist in the present moment. We always see their past. For nearby objects like the Moon, this delay is trivial, just over a second. For the Sun, it's 8 minutes. For HOPS 315, it's 13 centuries. For the most distant objects observable by our telescopes, galaxies billions of light years away, we see them as they existed when the universe was young, long before Earth even existed. Some of those distant galaxies may no longer exist at all, having long since evolved beyond recognition or merged with other galaxies. Yet we see them as they were, preserved in the light that has been traveling toward us across cosmic distances for billions of years. This temporal displacement adds a layer of poignancy to astronomical observation. We're always looking into the past, watching events that have already concluded by the time we observe them, but it also provides a unique capability by looking at objects at different distances. we're effectively looking at different moments in cosmic history. We can observe very young systems like HOPS 315 inches, their infancy, mature systems like our own in their middle age, and ancient systems in their twilight years, assembling a complete picture of stellar and planetary evolution. As we conclude our exploration of HOPS 315 and its significance for understanding planetary formation, we return to the fundamental realization that motivated this entire investigation. We are, all of us, products of planetary formation. Every atom in our bodies participated in the same processes we're now observing in that distant stellar system. 4.5 billion years ago, our solar system was in a state similar to what we observe in HOPS 315 today. A cloud of gas and dust, enriched with elements from previous stellar generations, collapsed under its own gravity. A protostar formed the infant Sunday, a protoplanetary disk spread outward, filled with swirling dust and gas. In that disk, silicon monoxide gas condensed into silicate crystals, just as we observe happening in HOPS 315. Those crystals accumulated into larger grains, then into pebbles, then into boulders, then into planetesimals. Those planetesimals collided and merged, building protoplanets. One of those protoplanets eventually became Earth. The story didn't end there. On that young Earth, covered in oceans and continents gradually taking shape, chemistry happened. Simple organic molecules formed and accumulated. Eventually, we don't know exactly how or when those molecules organized themselves into something we would recognize as alive. Life began. That early life was simple single-celled organisms, lacking nuclei, existing in a world without oxygen, surviving on chemical energy. But evolution proceeded generation after generation, mutation after mutation, over billions of years. Life grew more complex. Multicellular organisms evolved. Plants emerged and transformed the atmosphere, adding oxygen. Animals appeared and diversified. Mass extinctions periodically reset the evolutionary clock, but life persisted and adapted. Eventually, primates evolved. Within that primate lineage, a particular branch developed increasingly sophisticated brains capable of abstract thought, language, and symbolic reasoning. That branch became humanity. We learned to make tools, control fire, grow crops, build civilizations, develop writing, mathematics, and science. We learned to ask questions about the universe and develop methods to find answers. And now, representatives of that remarkable evolutionary lineage sit at computer screens, analyzing data from space telescopes, observing other worlds forming around distant stars, working to understand the processes that created us. The universe has developed the capacity to study itself, to understand its own nature and history. When we observe HOPS 315, we're not just watching an astronomical phenomenon. We're watching our own origin story playing out in another location. We're seeing the cosmic processes that made our existence possible, the deep history that led from formless gas clouds to living, thinking beings capable of contemplating their own origins. This perspective infuses the study of planetary formation with profound meaning. It's not just abstract astrophysics, it's the story of how we came to be, told through direct observation of the process happening elsewhere in the universe. And perhaps, billions of years from now, if intelligent life evolves in the HOPS 315 system, beings there will point their telescopes outward and observe our solar system. By that time, our sun will have exhausted its nuclear fuel and died, perhaps scattering its outer layers into space as a planetary nebula, leaving behind a slowly cooling white dwarf. Earth will be long gone, either incinerated when the sun swelled into a red giant or ejected into interstellar space. Those future observers around what was once HOPS 315 might study the remnants of our solar system, trying to understand how it formed and evolved. They might wonder, as we do, whether life ever emerged there. They might study the patterns in our asteroid belt, the spacing of planetary orbits, the composition of debris fields, piecing together our history from what remains. And they would never know that billions of years before their civilization emerged, beings on a planet in the solar system they're studying looked at their system when it was newly forming and witnessed the birth of worlds that would eventually give rise to them. The cosmic circle would be complete. We exist in the brief window between our solar system's birth and death, between the time when Earth became capable of supporting complex life and the time when the sun's evolution will render it uninhabitable. We've developed intelligence and technology during this window, allowing us to understand our cosmic context. We're privileged to live in an era when telescopes can peer across vast distances and observe other worlds forming, when we can finally answer questions about our origins that previous generations could only speculate about. The universe is vast, ancient, and largely indifferent to our existence. Yet that same universe, through the operation of natural laws over billions of years, has produced us beings capable of understanding it and appreciating its grandeur. We are the universe become conscious of itself, matter arranged in such a way that it can contemplate its own existence and seek to understand its own nature. As we study systems like HOPS 315, we're fulfilling the potential that emerged from our solar system's formation billions of years ago. We're using the capacity for understanding that evolution granted us to peer back into the cosmic past and witness the processes that made our existence possible. We're connecting the dots between distant astronomical observations and our own personal history, recognizing that we are intimately connected to the broader cosmos. We were once a swirling cloud of dust surrounding a young star, particles beginning to clump together under gravity's inexorable pull. Billions of years of evolution and change led from that cloud to conscious beings capable of observing similar clouds around other stars. And billions of years in the future, we'll return to dust scattered into space when our sun dies, eventually becoming part of new molecular clouds that will collapse to form new stars and planets, continuing the cosmic cycle. In the grand scheme of cosmic time, our individual lives, and even our entire civilization, represent the briefest of moments. Yet in that brief moment, we've achieved something remarkable. We've understood our origins, traced our history back to its cosmic roots, and observed the processes that created us happening elsewhere in the universe. We've answered questions that haunted our ancestors and made discoveries they could never have imagined possible. So perhaps, while we're here, conscious and capable of understanding, we should make the most of our brief existence. We should continue asking questions, seeking answers, pushing the boundaries of knowledge. We should appreciate the extraordinary fact of our existence and the remarkable universe that produced us. We should recognize our connection to the cosmos and our kinship with all life on Earth, all products of the same planetary formation process that we're now observing around HOPS 315. The universe has given us the capacity to understand it. The least we can do is use that capacity to the fullest, continuing the quest for knowledge that has characterized humanity throughout our history, honoring the cosmic processes that made us possible by striving to comprehend them as fully as we can. In the end, that may be the most profound significance of discovering HOPS 315 and observing planetary formation in progress. It connects us to the cosmos in the most direct way possible, showing us not just abstract astronomical phenomena, but the very processes that created our world and made our existence possible. It reminds us that we are not separate from the universe, but integral parts of it, products of cosmic evolution, temporarily organized collections of stardust, fortunate enough to be conscious during our brief existence. We are the universe contemplating itself, matter become aware, descendants of stellar death and planetary birth. And for this fleeting cosmic moment, we have the precious opportunity to understand our origins and appreciate the remarkable chain of events that led from formless gas clouds to conscious beings capable of studying those clouds around distant stars. That understanding and appreciation may be among the most meaningful achievements our species can claim during our temporary residence on this small planet. Orbiting an ordinary star in an unremarkable galaxy in a vast cosmos filled with wonders we're only beginning to comprehend.